Welcome to The Explainer. So let's talk about one of the most fundamental challenges in all of digital technology. How do you actually take something from the real world, like a sound wave or a radio signal, something that's infinitely detailed, and translate it into the language of ones and zeros that a computer can understand? This process, well, it's the foundation of pretty much everything, from your phone to medical imaging, and it all starts right here.
So here's what we're going to cover. We'll kick things off with signal sampling, which is really the first step in this whole digitization thing. Then we'll get into the supercritical Nyquist rule you absolutely have to follow. And we'll see what happens when you don't, this weird distortion called aliasing. After that, we'll tackle quantization, see how all this stuff shows up in the real world, and then we'll wrap it all up with the three big takeaways.
All right, first up, what is signal sampling? This is the very first step, the gateway from the analog world into a format that a computer can actually process.
At its core, sampling is basically taking snapshots of a continuous signal, like a sound wave, at really regular fixed points in time. It's these snapshots or samples that we use to build a digital picture of the original signal.
And this is a great way to visualize what's happening mathematically. So up top, you've got your smooth, continuous analog signal. Then we multiply it by this thing called an impulse train. You can just think of it like a perfect strobe light. Every single flash of that strobe captures the wave's exact amplitude at that one specific moment. And the result down at the bottom is our sampled signal, just a series of distinct data points that now represent that original wave.
Okay, so now we know what sampling is, but how do we know if we're taking those snapshots fast enough? Well, that leads us straight to the most important rule in this entire field, the Nyquist sampling rule. The secret to not losing information is this principle called the Nyquist-Shannon sampling theorem. And what it says is kind of remarkable. If you sample a signal fast enough, you can, at least in theory, perfectly reconstruct the original analog signal from just those discrete samples. Absolutely no information is lost. Now, to really get why this works, you've got to look at the signal in the frequency domain. So instead of time, we're looking at all the different frequencies that make up the signal. That top graph shows the frequency spectrum of our original signal. When we sample it, we create these perfect copies or replicas of that original spectrum. That's what you see on the bottom. The absolute key here is that clean space between the copies. That separation is what lets us perfectly isolate the original and rebuild the signal. And all of that boils down to this one simple, incredibly powerful formula. Your sampling frequency, Fs, must be greater than 2 times the maximum frequency in your signal, Fmax. This is the golden rule. You have to follow it. And this value, half of your sampling rate, is what we call the Nyquist frequency. It sets the hard upper limit for the frequencies your digital system can faithfully capture. Any frequency in the original signal that's higher than this is going to cause some major problems. So what happens when we break that rule? If we sample too slowly, we get this really destructive effect called aliasing. It's basically like your digital signal gets a mistaken identity. What happens with aliasing is your sampling rate is just too slow to catch the fast ups and downs of a high-frequency signal. And because of that, those high frequencies get disguised as lower frequencies in your data. And this isn't just a tiny error, it's a fundamental corruption of your information that you often can't fix. I love this analogy because it perfectly captures what's going on. A high-frequency signal literally puts on a low-frequency disguise. And once it's in your digital data, there is no way to know it was ever anything different. The perfect crime has just been committed on your signal. This side-by-side just makes the problem crystal clear. On the left, you've got proper sampling. See how the copies of the spectrum are cleanly separated? But on the right, that's what happens when you undersample. Notice how all the copies are just crammed together, overlapping and interfering with each other? That messy overlap, that is aliasing. And it means your original signal is now impossible to get back. Okay, so we've handled time by sampling. But there's another dimension we have to deal with, and that's amplitude. Right now, each of our samples still has a perfectly precise value, which, you guessed it, a computer can't store. And this brings us to our next big concept, quantization. So since a computer has to work with a finite number of bits, like 8-bit or 16-bit numbers, it just can't store an infinite range of values. Quantization is how we solve that. It's the process of mapping the continuous amplitude of each sample to a specific level from a limited predefined set of levels. And you can see exactly how it works here. The smooth, continuous amplitude of each sample gets snapped to the nearest available digital level. This is what creates that step-like approximation of the wave. Of course, the more levels you have, which comes from having more bits, the smaller those steps are and the more accurate your digital signal becomes.
And the process is really systematic. First, you figure out the maximum and minimum range of your signal. Second, you decide how many levels you're going to have based on the number of bits you're using. So for example, 8 bits gives you 2 to the power of 8, which is 256 levels. And finally, you just take each sample and assign it to whichever level is closest.
So why do we care about all this theory? Because these concepts, sampling, aliasing, and quantization, they are the invisible engines running inside pretty much all the modern tech we use every day. Let's look at a few examples. Seriously, it's everywhere, from the music you stream, to the phone call you make, to the medical scans that literally save lives. CT scanners, MRIs, digital cameras, they are all fundamentally based on correctly sampling and quantizing signals from the physical world.
Let's just grab one iconic example, digital audio. You've probably seen this number before, 44.1 kilohertz. It's famous as the sampling rate for audio CDs. And the reason for this very specific number is a perfect real-world application of everything we've just talked about.
So the upper limit of human hearing is generally considered to be about 20 kilohertz. To satisfy the Nyquist theorem, we need a sampling rate of at least double that, so at least 40 kilohertz. The CD standard uses 44.1 kilohertz, which gives us a nice little buffer and makes sure that all the frequencies we can possibly hear are captured perfectly, with no aliasing.
All right, we've gone through a lot, so let's boil it all down to the 3 absolute core concepts you need to walk away with about this whole analog to digital conversion process. Remember these 3 steps. First, you sample in time. That's how you go from continuous to discrete. Second, you have to obey the Nyquist rule, sample more than twice as fast as your highest frequency, or else you get that catastrophic aliasing error. And third, you quantize the amplitude of those samples so they can finally be represented by a finite number of bits. Now that you get these concepts, you'll start seeing them everywhere. Think about high-speed video trying to capture fast motion without blur, or complex radio signals for our phones and Wi-Fi, or even the sensors in your car that are constantly measuring engine performance. The principles are exactly the same. And now you have the tools to understand how it all actually works.